Learning objectives. In this chapter, the user will learn the following in detail. Exploration of websites on data warehousing and data mining applications, including bibliography of databases, corporate houses and research labs, use of data mining packages and data warehousing packages, for example, SAS, IBM, Excel miner tools. Exploration of websites on data warehousing and data mining application, including bibliography databases, corporate houses, and research labs. We will now examine several application domains for data warehouse and data mining. The figure shows the common data mining application domains. Data mining for financial data analysis. Most banks and financial institutions offer a wide variety of banking, investment, and credit services. The latter include business, mortgage, and automobile loans and credit cards. Some also offer insurance and stock investment services. Financial data collected in the banking and financial industry are often relatively complete, reliable, and of high quality, which facilitates systematic data analysis and data mining. Here we present a few typical cases. Design and construction of data warehouses for multidimensional data analysis and data mining. Loan payment prediction and customer credit policy analysis. Classification and clustering of customers for targeted marketing. Detection of money laundering and other financial crimes. Design and construction of data warehouses for multidimensional data analysis and data mining. Like many other applications, data warehouses need to be constructed for banking and financial data. Multidimensional data analysis methods should be used to analyze the general properties of such data. For example, a company's financial officer may want to view the debt and revenue changes by month, region, and sector, and other factors along with the maximum, minimum, total, average, trend, deviation, and other statistical information. Data warehouses, data cubes, including advanced data cube concepts such as multi-feature, discovery-driven, regression and prediction data cubes, characterization and class comparisons, clustering and outlier analysis will all play important roles in financial data analysis and mining. Loan payment prediction and customer credit policy analysis. Loan payment prediction and customer credit analysis are critical to the business of a bank. Many factors can strongly or weakly influence it. Data mining methods such as attribute selection and attribute relevance ranking may help identify important factors and eliminate irrelevant ones. For example, factors related to the risk of loan payments include loan-to-value ratio, term of the loan, debt ratio, total amount of monthly debt versus total monthly income, payment-to-income ratio, customer income level, education level, residence region, and credit history. Analysis of the customer payment history may find that, say, payment-to-income ratio is a dominant factor, while education level and debt ratio are not. The bank may then decide to adjust its loan granting policy so as to grant loans to those customers whose applications were previously denied but whose profiles show relatively low risks according to the critical factor analysis. Classification and clustering of customers for targeted marketing. Classification and clustering methods can be used for customer group identification and targeted marketing. For example, we can use classification to identify the most crucial factors that may influence a customer's decision regarding banking. Customers with similar behaviors regarding loan payments may be identified by multidimensional clustering techniques. These can help identify customer groups, associate a new customer with an appropriate customer group, and facilitate targeted marketing. Detection of money laundering and other financial crimes. To detect money laundering and other financial crimes, it is important to integrate information from multiple heterogeneous databases. For example, bank transaction databases and federal or state crime history databases, as long as they are potentially related to the study. Multiple data analysis tools can then be used to detect unusual patterns, such as large amounts of cash flow at certain periods by certain groups of customers. Useful tools include data visualization tools to display transaction activities using graphs by time and by groups of customers, linkage and information network analysis tools to identify links among different customers and activities, classification tools to filter unrelated attributes and rank the highly related ones, clustering tools to group different cases, outlier analysis tools to detect unusual amounts of fund transfers or other activities, and sequential pattern analysis tools to characterize unusual access sequences. These tools may identify important relationships and patterns of activities and help investigators focus on suspicious cases for further detailed examination. Data mining for retail and telecommunication industries. The retail industry is a well-fit application area for data mining since it collects huge amounts of data on sales, customer shopping history, goods transportation, consumption, and service. The quantity of data collected continues to expand rapidly, especially due to the increasing availability, ease, and popularity of business conducted on the web or e-commerce. Today, most major chain stores also have websites where customers can make purchases online. Some businesses, such as Amazon.com, www.amazon.com, exist solely online without any physical store locations. Retail data provide a rich source for data mining. Retail data mining can help identify customer buying behaviors, discover customer shopping patterns and trends, improve the quality of customer service, achieve better customer retention and satisfaction, enhance goods consumption ratios, design more effective goods transportation and distribution policies, and reduce the cost of business. A few examples of data mining in the retail industry are outlined as follows. Design and construction of data warehouses. Because retail data cover a wide spectrum, including sales, customers, employees, goods transportation, consumption, and services, there can be many ways to design a data warehouse for this industry. The levels of detail to include can vary substantially. The outcome of preliminary data mining exercises can be used to help guide the design and development of data warehouse structures. This involves deciding which dimensions and levels to include and what pre-processing to perform to facilitate effective data mining. Multi-dimensional analysis of sales, customers, products, times, and region. The retail industry requires timely information regarding customer needs, product sales, trends, and fashions, as well as the quality, cost, profit, and service of commodities. It is therefore important to provide powerful multidimensional analysis and visualization tools, including the construction of sophisticated data cubes according to the needs of data analysis. The advanced data cube structures are useful in retail data analysis because they facilitate analysis on multidimensional aggregates with complex conditions. Analysis of the effectiveness of sales campaigns. The retail industry conducts sales campaigns using advertisements, coupons, and various kinds of discounts and bonuses to promote products and attract customers. Careful analysis of the effectiveness of sales campaigns can help improve company profits. Multidimensional analysis can be used for this purpose by comparing the amount of sales and the number of transactions containing the sales items during the sales period versus those containing the same items before or after the sales campaign. Moreover, association analysis may disclose which items are likely to be purchased together with the items on sale, especially in comparison with the sales before or after the campaign. Customer retention, analysis of customer loyalty. We can use customer loyalty card information to register sequences of purchases of particular customers. Customer loyalty and purchase trends can be analyzed systematically. Goods purchased at different periods by the same customers can be grouped into sequences. Sequential pattern mining can then be used to investigate changes in customer consumption or loyalty and suggest adjustments on the pricing and variety of goods to help retain customers and attract new ones. Product recommendation and cross-referencing of items. By mining associations from sales records, we may discover that a customer who buys digital camera is likely to buy another set of items. Such information can be used to form product recommendations. Collaborative recommender systems use data mining techniques to make personalized product recommendation during live customer transactions based on the opinions of other customers. Product recommendations can also be advertised on sales receipts, in weekly flyers, or on the web to help improve customer service, aid customers in selecting items, and increase sales. Similarly, information such as hot items this week or attractive deals can be displayed together with the associated information to promote sales. Fraudulent analysis and identification of unusual patterns. Fraudulent activity costs the retail industry millions of dollars per year. It is important to 1. Identify potentially fraudulent users and their atypical usage patterns. 2. Detect attempts to gain fraudulent entry or unauthorized access to individual and organizational accounts. And 3. Discover unusual patterns that may need special attention. Many of these patterns can be discovered by multidimensional analysis, cluster analysis, and outlier analysis. As another industry that handles huge amounts of data, the telecommunication industry has quickly evolved from offering local and long-distance telephone services to providing many other comprehensive communication services. These include cellular phone, smartphone, internet access, email, text messages, images, computer and web data transmissions, and other data traffic. The integration of telecommunication, computer network, internet, and numerous other means of communication and computing has been underway, changing the face of telecommunications and computing. This has created a great demand for data mining to help understand business dynamics, identify telecommunication patterns, catch fraudulent activities, make better use of resources, and improve service quality. Data mining tasks in telecommunications share many similarities with those in the retail industry. Common tasks include constructing large-scale data warehouses, performing multidimensional visualization, overlap and in-depth analysis of trends, customer patterns, and sequential patterns. Such tasks contribute to business improvements, cost reduction, customer retention, fraud analysis, and sharpening the edges of competition. There are many data mining tasks for which customized data mining tools for telecommunication have been flourishing and are expected to play increasingly important roles in business. Data mining has been popularly used in many other industries, such as insurance, manufacturing, and healthcare, as well as for the analysis of governmental and institutional administration data. Although each industry has its own characteristic data sets and application demands, they share many common principles and methodologies. Therefore, through effective mining in one industry, we may gain experience and methodologies that can be transferred to other industrial applications. Data mining in science and engineering. In the past, many scientific data analysis tasks tended to handle relatively small and homogeneous data sets. Such data were typically analyzed using a formulate hypothesis, build model, and evaluate results paradigm. In these cases, statistical techniques were typically employed for their analysis. Massive data collection and storage technologies have recently changed the landscape of scientific data analysis. Today, scientific data can be amassed at much higher speeds and lower costs. This has resulted in the accumulation of huge volumes of high-dimensional data, stream data, and heterogeneous data containing rich spatial and temporal information. Consequently, scientific applications are shifting from the hypothesis and test paradigm toward a collect and store data, mine for new hypotheses, confirm with data or experimentation process. This shift brings about new challenges for data mining. Vast amounts of data have been collected from scientific domains, including geosciences, astronomy, meteorology, geology, and biological sciences, using sophisticated telescopes, multispectral high-resolution remote satellite sensors, global positioning systems, and new generations of biological data collection and analysis technologies. Large datasets are also being generated due to fast numeric simulations in various fields such as climate and ecosystem modeling, chemical engineering, fluid dynamics, and structural mechanics. Here we look at some of the challenges brought about by emerging scientific applications of data mining. Data warehouses and data pre-processing. Data pre-processing and data warehouses are critical for information exchange and data mining. Creating a warehouse often requires finding means for resolving inconsistent or incompatible data collected in multiple environments and at different time periods. This requires reconciling semantics, referencing systems, geometry measurements, accuracy, and precision. Methods are needed for integrating data from heterogeneous sources and for identifying events. For instance, consider climate and ecosystem data, which are spatial and temporal and require cross-referencing geospatial data. A major problem in analyzing such data is that there are too many events in the spatial domain but too few in the temporal domain. For example, El Nino events occur only every 4 to 7 years, and previous data on them might not have been collected as systematically as they are today. Methods are also needed for the efficient computation of sophisticated spatial aggregates and the handling of spatial-related data streams. Mining complex data types. Scientific data sets are heterogeneous in nature. They typically involve semi-structured and unstructured data, such as multimedia data and georeference stream data, as well as data with sophisticated, deeply hidden semantics, and proteomic data. Robust and dedicated analysis methods are needed for handling spatio-temporal data, biological data, related concept hierarchies, and complex semantic relationships. For example, in bioinformatics, a research problem is to identify regulatory influences on genes. Gene regulation refers to how genes in a cell are switched on or off to determine the cell's functions. Different biological processes involve different sets of genes acting together in precisely regulated patterns. Thus, to understand a biological process, we need to identify the participating genes and their regulators. This requires the development of sophisticated data mining methods to analyze large biological data sets for clues about regulatory influences on specific genes by finding DNA segments, regulatory sequences mediating such influence. Graph-based and network-based mining. It is often difficult or impossible to model several physical phenomena and processes due to limitations of existing modeling approaches. Alternatively, labeled graphs and networks may be used to capture many of the spatial, topological, geometric, biological, and other relational characteristics present in scientific datasets. In graph or network modeling, each object to be mined is represented by a vertex in a graph, and edges between vertices represent relationships between objects. For example, graphs can be used to model chemical structures, biological pathways, and data generated by numeric simulations such as fluid flow simulations. Visualization tools and domain-specific knowledge. High-level graphical user interfaces and visualization tools are required for scientific data mining systems. These should be integrated with existing domain-specific data and information systems to guide researchers and general users in searching for patterns, interpreting and visualizing discovered patterns, and using discovered knowledge in their decision-making. Data mining for intrusion detection and prevention. The security of our computer systems and data is at continual risk. The extensive growth of the Internet and the increasing availability of tools and tricks for intruding and attacking networks have prompted intrusion detection and prevention to become a critical component of network systems. An intrusion can be defined as any set of actions that threaten the integrity, confidentiality, or availability of a network resource. For example, user accounts, file systems, system kernels, and so on. Intrusion detection systems and intrusion prevention systems both monitor network traffic and/or system executions for malicious activities. However, the former produces reports, whereas the latter is placed in line and is able to actively prevent or block intrusions that are detected. The main functions of an intrusion prevention system is to identify malicious activity, log information about said activity, attempt to block or stop activity, and report activity. The majority of intrusion detection and prevention systems use either signature-based detection or anomaly-based detection. New data mining algorithms for intrusion detection. Data mining algorithms can be used for both signature-based and anomaly-based detection. In signature-based detection, training data are labeled as either normal or intrusion. A classifier can then be derived to detect known intrusions. Research in this area has included the application of classification algorithms, association rule mining, and cost-sensitive modeling. Anomaly-based detection builds models of normal behavior and automatically detects significant deviations from it. Methods include the application of clustering, outlier analysis, and classification algorithms and statistical approaches. Associations, correlation, and discriminative pattern analyses help select and build discriminative classifiers. Association, correlation, and discriminative pattern mining can be applied to find relationships between system attributes describing the network data. Such information can provide insight regarding the selection of useful attributes for intrusion detection. New attributes derived from aggregated data may also be helpful, such as summary counts of traffic matching a particular pattern. Analysis of stream data. Due to the transient and dynamic nature of intrusions and malicious attacks, it is crucial to perform intrusion detection in the data stream environment. Moreover, an event may be normal on its own but considered malicious if viewed as part of a sequence of events. Thus, it is necessary to study what sequences of events are frequently encountered together, find sequential patterns, and identify outliers. Other data mining methods for finding evolving clusters and building dynamic classification models in data streams are also necessary for real-time intrusion detection. Distributed data mining. Intrusions can be launched from several different locations and targeted to many different destinations. Distributed data mining methods may be used to analyze network data from several network locations to detect these distributed attacks. Visualization and querying tools. Visualization tools should be available for viewing any anomalous patterns detected. Such tools may include features for viewing associations, discriminative patterns, clusters, and outliers. Intrusion detection systems should also have a graphical user interface that allows security analysts to post queries regarding the network data or intrusion detection results. Applications in library and information service. Bibliomining. Most people think of libraries as a little brick building in the heart of their community, or the big brick building in the center of a campus. These notions greatly oversimplify the world of libraries, however. With the increasing use of the Internet and the World Wide Web, digital libraries have proliferated, and these serve a huge variety of different user audiences. For example, people interested in health and medicine, science and technology, industry and world news, law and business. With this expanded view of libraries, two key insights arise. First, libraries are nearly always embedded within larger institutions. Corporate libraries serve their corporations, academic libraries serve their universities, and public libraries serve the general public. Second, libraries play an important role with their institutions as repositories and providers of information resources. This fact provides the basis for the strategic importance of library data mining. By ascertaining what users need to know and how well those needs are served, bibliomining can reveal insights that have meaning in the context of the library's host institution. Using bibliomining, libraries can ascertain what their constituencies want to learn, whether they find the information they seek, and whether that information satisfies their learning and knowledge needs. Bibliomining to improve library services. Most libraries exist to serve the information needs of users, and therefore understanding those needs is crucial to libraries' success. Examining the behaviors of a large group of users for regular patterns can allow the library to have a better idea of the information needs of their user base and therefore better customize the library services to meet those needs. For many decades, libraries have provided readers' advisory services with the help of librarians who know the collection well enough to help a user choose a work similar to the other works. Market analysis can provide the same function by examining circulation histories to locate related works. Predict future needs. By looking for patterns in high-use items, librarians can better predict the demand for new items in order to determine how many copies of a work to order. To prevent inventory loss, predictive modeling can be used to look for patterns commonly associated with lost or stolen books and higher user fees. Once these patterns have been discovered, appropriate policies can be put in place to reduce inventory losses. In addition, fraud models can be used to determine the appropriate course of action for users who are chronically late in returning materials. The library can also better serve their user audience by determining areas of deficiency in the collection. The reference desk and the OPAC are two sources of data that can aid in solving problems with the collection. If the topics or questions asked at the reference desk are recorded along with the perceived outcome of the interaction, then patterns can be discovered to guide librarians to areas that need attention in the collection. Role of data warehousing and data mining in decision. The goals of a data warehouse here is to support decision making with data. Data mining can be used in conjunction with a data warehouse to help with certain types of decisions. To be successful, data warehousing and data mining needs a skilled user who will supply the correct data and a specialist who can make objective conclusions out of the output that is created. If the user supplies incorrect or minimal amount of information, output will be affected and the forecast will not be credible. Data warehousing provides answers of many queries to the organization and the user and helps in decision making. There are many types of queries of the organization like tactical query, strategic query, and update query. A tactical query is a database operation that attempts to determine the best course of action right now. A tactical query provides information to rank and file elements in the field that need to respond quickly to a set of unfolding events. Tactical queries tend to produce a very small result set. It is not uncommon for the result set to be less than a dozen rows. Usually the result set is designed to fit into a single window on a display screen, whereas the strategic query provides the information necessary to make long-term business decisions. A strategic query is a database operation that attempts to determine what has happened, why it happened, and or what will happen next. It typically accesses vast amounts of detailed data from the warehouse and ranges in complexity from simple table scans to multi-way joins and subqueries. Applications that generate strategic queries include report generation, OLAP, decision support, ad hoc data mining, etc. Use of data mining packages and data warehousing packages, for example, SAS, IBM, Excel Miner tools. Introduction to SAS Enterprise Miner. SAS Enterprise Miner is an advanced analytics data mining tool intended to help users quickly develop descriptive and predictive models through a streamlined data mining process. Enterprise Miner's graphical interface enables users to logically move through the data mining process using the 5-step SAS SEMMA approach: sampling, exploration, modification, modeling, and assessment. Users can build a process flow by selecting the appropriate tab from Enterprise Miner's toolbar and then dragging and dropping step-specific nodes onto a palette. Enterprise Miner supports several algorithms and techniques, including decision trees, time series, neural networks, linear and logistic regression, sequence and web path analysis, market basket analysis, and link analysis. Enterprise Miner's client-server architecture lets business users and data analysts collaborate and share models and other work. SAS Enterprise Miner features. SAS Rapid Predictive Modeler is a component of SAS Enterprise Miner that can run as an add-in to Microsoft Excel, allowing business users to perform predictive modeling directly from within their Excel spreadsheets. Models developed in Rapid Predictive Modeler can be customized by data analysts using Enterprise Miner. Support for in-database and in-Hadoop scoring. When combined with the SAS Scoring Accelerator, scoring algorithms created in SAS Enterprise Miner can be deployed and executed within a database or Hadoop environment. Scoring accelerators are available for Hadoop, Pivotal Green Plum, DB2, IBM Netessa, Oracle, Teradata, and SAS Scalable Performance Data Server. The figure shows sample, explore, modify, model, and assess steps. Overview of the data. A typical data set has many thousand observations. An observation may represent an entity such as an individual customer, a specific transaction, or a certain household. Variables in the data set contain specific information such as demographic information, sales history, or financial information for each observation. How this information is used depends on the research question of interest. When talking about types of data, consider the measurement level of each variable. You can generally classify each variable as one of the following. Interval, a variable for which the mean or average makes sense, such as average income or average temperature. Categorical, a variable consisting of a set of levels, such as gender, male or female, or drink size, small, regular, large. Subgroupings, unary, binary, nominal, ordinal. Predictive and descriptive techniques. Predictive modeling techniques enable you to identify whether a set of input variables is useful in predicting some outcome variable. For example, a financial institution may try to determine if knowledge of an applicant's income and credit history, input variables, helps to predict whether the client is likely to default on a loan, outcome variable. Descriptive techniques enable you to identify underlying patterns in a data set. These techniques do not have a specific outcome variable of interest. Cluster analysis. This analysis attempts to find natural groupings of observations in the data based on a set of input variables. After grouping the observations into clusters, you can use the input variables to try to characterize each group. When the clusters have been identified and interpreted, you can decide whether to treat each cluster independently. Association analysis. This analysis identifies groupings of products or services that tend to be purchased at the same time or at different times by the same customer. Overview of SEMMA. Enterprise miner nodes are arranged in the following categories according to the SAS process for data mining. SEMMA. Sample, identify input data sets, identify input data, sample from a larger data set, partition data set into training, validation, and test data sets. Explore. Explore data sets statistically and graphically. Plot the data, obtain descriptive statistics, identify important variables, perform association analysis. Modify. Prepare the data for analysis. Create additional variables or transform existing variables for analysis. Identify outliers. Replace missing values. Modify the way in which variables are used for the analysis. Perform cluster analysis. Analyze data with self-organizing maps known as SOMs or cohorted networks. Model. Fit a predictive model. Model a target variable by using a regression model, a decision tree, a neural network, or a user-defined model. Assess. Compare competing predictive models. Build charts that plot the percentage of respondents captured, lift, and profit. IBM Intelligent Miner. IBM has put significant research effort into its Intelligent Miner for Data product, which runs on Windows NT, OS 400, Unix, and OS 390, and can process data stored in DB2 family databases, any relational database supported by a data joiner, and flat files. Intelligent Miner version 1, released in 1996, enabled users to mine structured data stored in relational databases and flat files and offered a wide range of different mining algorithms. Intelligent Miner version 2 features a new graphical interface, additional mining algorithms, DB2 universal database exploitation, and improved parallel processing. Intelligent Miner has good data visualization capabilities and, unlike many other mining tools, supports several information mining algorithms. The Intelligent Miner IM helps us perform data mining tasks. Through an intuitive graphical user interface GUI, you can visually design data mining operations. In addition, IM selects data, explores it, transforms it, and visually interprets the results for productive and efficient knowledge discovery. Overview of the Intelligent Miner. The IM is based on a client-server architecture. The server executes mining and processing functions and can host historical data and mining results. The client is powered with administrative and visualization tools and can be used to visually build a data mining operation, execute it on the server, and have the results returned for visualization and further analysis. In addition, the IM Application Programming Interface API provides C++ classes and methods as well as C structures and functions for application programmers. Working with databases. Most functions of the IM can use input data from either flat files or database tables. If you want to access DB2 tables, you only require authorization to access that database and the permission to query the appropriate tables. If you want to access files in Oracle, SPSS, or SAS format, Data Joiner may be installed as a middleware product. There are two ways to access database management systems. Connect through the Intelligent Miner server without installing any database software in the client. Connect directly from the client to the table, letting the IAM client access the database without using the IAM communication interface. The user interface. The IAM helps businesses reduce the cost of data mining and maximize the return on investment, ROI, providing an administrative user interface based on Java. The IAM user interface is simple and intuitive and provides consistency across all operations. The interface's state-of-the-art GUI facilities include online help, task guides, and a graphical representation of the mining operations and its functions. Data preparation functions. Once the desired database tables have been selected and the data to be mined has been identified, it is usually necessary to perform certain transformations on the data. IAM provides a wide range of data preparation functions which help to optimize the performance of the data mining functions. Depending on the data mining technique, you can select, sample, aggregate, filter, cleanse, and/or transform data in preparation for mining. The data preparation functions are aggregate values, calculate values, clean up data sources, convert to lower or uppercase, copy records to file, discard records with missing values, discretize into quantiles, discretize using ranges, encode missing values, encode non-valid values, filter fields, filter records using a value set. Data preparation functions are performed through the GUI, reducing the time and complexity of data mining operations. You can transform variables, impute missing values, and create new fields through the touch of a button. This automation of the most typical data preparation tasks is aimed at improving your productivity by eliminating the need for programming specialized routines. Statistical and mining functions. After transforming the data, we use one or more data mining functions in order to extract the desired type of information. IAM provides both statistical analysis tools and state-of-the-art machine learning algorithms for successful data mining. Statistical functions facilitate the analysis and preparation of data, as well as providing forecasting capabilities. For example, you can apply statistical functions like regression to understand hidden relationships in the data, or use factor analysis to reduce the number of input variables. Statistical functions include factor analysis, linear regression, principal component analysis, univariate curve fitting, univariate and bivariate statistics. Based on IBM research, validated through real-world applications, IAM has incorporated a number of data mining algorithms as the critical suite to address the wide range of business problems. The algorithms are categorized as follows. Association discovery. Given a collection of items and a set of records, each of which contains some number of items from the given collection, an association discovery function is an operation against this set of records which returns affinities that exist. Sequential pattern discovery. A sequence discovery function will analyze collections of related records and will detect frequently occurring patterns of products bought over time among the collection of items. Clustering. Clustering is used to segment a database into subsets, the clusters with the members of each cluster sharing a number of interesting properties. Classification. Classification is the process of automatically creating a model of classes from a set of records. The induced model consists of patterns, essentially generalizations over the records that are useful for distinguishing the classes. Once a model is induced, it can be used to automatically predict the class of other unclassified records. Value prediction. As in classification, the goal is to build a data model as a generalization over the records. However, the difference is that the target is not a class membership, but an actual value. Similar time sequences. The purpose of this process is to discover all occurrences of similar subsequences in a database of time sequences. Conclusion. In this chapter, we have covered the following in detail. Exploration of websites on data warehousing and data mining applications, including bibliography databases. corporate houses and research labs, use of data mining packages and data warehousing packages, for example, SAS, IBM, Excel Miner tools.